Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss reflection and refraction of plane waves at plane interface between two media. Means we can prove laws of reflection and refraction by using electromagnetic waves at plane interface between two media. Let's begin. First, we have to consider two medium. It has medium 1 there medium 2, that the medium 1 has permittivity epsilon 1, permeability mu 1 and refractive index n1. Similarly, medium 2 permittivity epsilon 2, permeability mu 2, refractive index n2. That one is the interface between the two media, and in coordinate system we say it is x axis, normal is drawn, that as z axis, this is the interface. Let us take a plane wave is incident at the interface separating the two media, medium 1 and medium 2. This is the incident wave. That incident wave incidenting on that of interface between that of two media is partially reflected and partially refracted. Or we can say that is transmitted. See the reflected wave, that one is transmitted wave. Transmitted wave or refracted wave, and that incident wave, technically we show it by the wave vector that is given as k I for incident wave and k r for reflected wave. This is refracted wave or transmitted wave. As r sign is used, it is very easy To detect that transmitted wave or refracted wave, we can use the letter as T, this K T, transmitted wave. That incident wave making an angle to that of normal is the angle of incident, that angle of incident theta I, and angle of reflection, angle in between reflected and normal, theta r. Next, angle between refracted or transmitted wave to that of normal, angle of transmitted wave, that is theta t. This is the incidence of plane electromagnetic wave. As you know, electromagnetic wave is nothing but electric field vector and magnetic field vector. Here we prefer electric field vector for our calculation. Let us choose electric field vector of that plane electromagnetic wave and that electric field vector is given as E vector is equal to E naught vector into e to the power I k dot r minus omega t. Now we can write that electric field vector for incident wave, reflected wave and transmitted wave. Therefore, for incident wave, it is written as E I, that with the notation. So E0 I e to the power I, that is ki dot r minus omega I t. Next, for reflected wave, for reflected wave, it is E r vector as E O r e to the power I k r dot r vector omega r t. Same for transmitted wave, E t vector is equal to E O t vector dot e to the power I k t vector dot r vector omega t t. Equation number 2, 3 and 4. as we use the interface that separating the two media for that of electromagnetic wave, since we prefer electric field vector of that electromagnetic wave, then we can use the boundary condition for electric field vector on that interface. So, what is the boundary condition? The boundary condition for electric field vector is the tangential component of electric field is continuous across the interface between two media, means the tangential component of electric field on that medium 1 is same as the tangential component of electric field on that of medium 2. We write here from the boundary condition that the tangential component of electric field is continuous across the interface between the media, that is the tangential component of electric field and that of medium 1 is same as the tangential component of electric field at medium 2. Here the tangential component at medium 1 due to the tangential component of incident wave and the tangential component of reflected wave. So, we write the tangential component of incident wave as E I vector tangential plus E R vector tangential is same to that of E T vector tangential. The tangential component of electric field at medium 1 is same as the tangential component of electric field at medium 2. At medium 1, this is due to that incident wave and reflected wave, and in medium 2 it is due to only transmitted wave. So, using the values EI tangential component as E 0I tangential component into e to the power I ki that r minus omega I t plus, just use the value of EI vector, its tangential component on that one. Next, tangential component for ER vector, its tangential into e to the power I kr omega r t is equal to, next for ET vector, that is E 0t tangential e to the power I k t r omega t r. The equation number 5. We have already known that equation is valid, and we can say the property of that type of equation is these are independent of position and time. Means if I change the position at any point of that interface, that equation is valid. Same thing at any point and at any time also that equation is satisfied. That indicates that equation is independent of position and time. The above equation the property of above equation is that the position and time are independent to that equation. Therefore, choosing that of position section, first choosing that of time section, omega I t is equal to omega r t is equal to omega t t, or omega I is equal to omega r is equal to omega t, all are same. Let us say that is omega. First, what it signifies? It signifies all the three waves, incident wave, reflected wave and refracted waves, all the three waves have same frequency, okay. All the three waves have same frequency. Again taking the position 1 as ki dot r, here we choose that interface, the component of electric field continuous across the interface between the media. That interface, where is the interface? Whereas z is equal to 0, interface, that is z is equal to 0. Therefore, ki dot r vector as z is equal to 0. Next, kr dot r vector at z is equal to 0, kt r vector at z is equal to 0. So, what is k vector dot product with r vector? As we say, k vector when dot product with r vector, we obtain kx x, ky y, kz z. But when it is indicating that z component is 0, similarly for that of I we can use, for I it is k ix into x, k iy into y, k iz into z, but z component will be 0. So only x and y component exist. So that value as k ix x plus k iy into y, that is ki dot r vector, is equal to, for that one kr dot r vector as k rx x plus k ry y is equal to, for kt vector dot r vector k tx x k ty dot y. Okay. Now comparing these equations, as its x component is same as this x components and see y components same to that of y components. So k ix is equal to k rx is equal to k tx, and its y components k iy is equal to k ry is equal to k ty. Let's refer it as equation number 5 and equation number 6. Again, as we say, at the interface z is equal to 0. So the incident wave at what plane? At x z plane. At x z plane, the ith component will be, the yth component will be 0. Now it can be shown that but the incident beam is in xz plane, then y component k iy is equal to 0. So that equation as k iy is equal to 0, 0 is equal to k ry k ty, that is equation number as 6. Okay. From that of equation number 5, here ix, rx and tx, what it indicates means the incident wave, reflected wave and transmitted wave are in a same plane. From that of equation number 5 and 6, from that equation number 5 and 6, it is clear that the incident reflected and refracted waves and the normal to the interface all lie in the same plane. The incident reflected and refracted waves and normal to that of interface all lie in same plane. It is clear from that of equation number 5 and equation number 6, as its x component of incident, x component of reflected and x component of transmitted wave are equal and y components are now 0, then we can say all are in a same plane. This is the law of reflection and refraction, one of the law of reflection and refraction. Next, again k vector in case of incident reflected and transmitted can be evaluated in terms of normal and tangential components as, come to that figure, this is the incident wave. For incident wave, let us choose for incident wave, this is for incident wave, that is ki, that creates an angle theta I, which is angle of incident. So this angle as theta I. Now using vector resolution, that section as k I cos theta I and this section as k I sin theta I, which is nothing but x component of that incident k I x. Next, for reflected wave, that with the propagation vector kr, see the propagation vector kr, that angle as theta. So this component kr cos theta, that component kr sin theta, which is nothing but x component of that reflected wave, which is k rx. Next, for transmitted wave, this is the transmitted wave vector kt, it creates an angle theta t. We resoluate that vector as k t cos theta t. Here is k t sin theta t, and the x component of that transmitted vector k tx, which is the x component k tx. Now, from that equation number 5th, from equation number 5th, it is k ix is equal to k rx. What is kix? Ki sin theta I, ki sin theta I. What is krx? Kr sin theta, kr sin theta. Here in that figure, ki and kr are in the same medium 1. Therefore, the propagation vector value will be same. Since ki and kr are in same medium, so they are equal. So ki and kr cancelled out. So we obtain sin theta I is equal to sin theta, they are equal, as ki is equal to kr. So theta of I is equal to theta of r. What it clarifies? The angle of incidence is equal to angle of reflection. This is the angle of incidence is equal to the angle of reflection, which is the law of reflection, the law of reflection. Angle of incidence is equal to angle of reflection, which is the law of reflection. Next, in case of law of refraction, we can prove that is Snell's law. Again, from that of equation number 5, here that kix is equal to ktx. Again, from equation 5, k ix is equal to k tx. Similarly, k ix, ki sin theta I, ki sin theta I, k tx, kt sin theta t, kt sin theta t. But here, as we say, ki is equal to omega divided by v1. v1 is the velocity of that electromagnetic waves in that of medium 1, which is omega divided by, in place of velocity, that is 1 by under root of mu 1 epsilon 1 in medium 1. This is the this is the permeability, this is the permittivity, which is equal to ki is equal to omega into mu 1 epsilon 1 under root. Similarly, for kt, that is omega by v2, the transmitted wave on that of medium 2. At medium 2, it is omega divided by 1 divided by mu 2 epsilon 2 under root. Therefore, kt is equal to omega into mu 2 epsilon 2 under root. So, these values are put here. This is sin theta, this is sin theta t, sin theta t. So, sin theta I divided by sin theta t is equal to k t divided by k I, or kt as kt omega mu 2 epsilon 2 under root divided by ki omega mu 1 epsilon. Why we choose omega as same? As we derive an equation as angular frequencies are same for that of 3 waves. Therefore, in medium 1 and medium 2, omega is same. So, omega cancelled out, which is sin theta I divided by sin theta t. Look here, as we know, the refractive index definition, n1 is equal to mu 1 epsilon 1 under root, and n2 mu 2 epsilon 2 under root. These are the refractive indexes of medium 1 and medium 2, medium 1 and 2 respectively. Therefore, sin theta I divided by sin theta t is equal to n2 divided by n1. That one as nothing but Snell's law. This is Snell's law. The sine of angle of that incident to that of sine of angle of that refraction is nothing but a constant, which is the refractive index of that of medium with respect to another. This is law of reflection, that is law of refraction. Hence, we can say law of reflection. Therefore, the law of reflection and refraction are proved by taking the propagation of plane EM waves at the interface separating two media. Okay. So here with the help of this video lecture we understand reflection and refraction of plane waves at interface between two media means the proof of laws of reflection and refraction using that of electric field vector for electromagnetic wave, for incident wave, reflected wave and transmitted wave. Then use the boundary condition for that of electric field vector. That equation is indicating that the position and time are independent, then the frequencies are same. Next, it is show that incident, reflected and refracted waves are normal to that of interface, all lie in same plane. For incident wave, reflected wave and refracted wave, from that of equation it is clear that the angle of incidence is equal to the angle of reflection, which is the law of reflection. Again it can be shown the Snell's law, and finally we prove laws of reflection and refraction by taking the propagation of electromagnetic waves at the interface which separating the two media. So with this useful and informative notes, let me wind up the session. Thank you.